In this lecture, we're going to talk about magnetic induction. So some important things to understand that we have already talked about. Current is generated by changing a magnetic field. So when we have a changing magnetic field, that will make electrons move. Also, a magnetic field is created by a changing current. So if we have electrons moving in a current, like their overall position is changing, then that will create a magnetic field. We saw this by the current carrying wire deflecting the compass needle. So first let's talk about motional EMF. Remember, EMF is basically just change in difference in potential between two places. So we have a conductor of length L. So this is my conductor, this yellow piece. Its length is L. And it moves at a velocity v through a uniform magnetic field. There are charges that are free to move because it's a conductor, and because of that motion in the magnetic field, there's going to be a force on those charges. So we can use the right-hand rule to determine which way that force is. So if you put your thumb in the direction of the velocity, which is to the right, you put your fingers in the direction of the magnetic field, which is, these are X's, so it's into the page. Your palm should be facing up. The force on those positive charges is up. So positive charges are going to move to the top of this plate or wire or whatever it is. Negative charges are going to move to the bottom. And because of that separation of charge, we are going to get an electric field, which will also put a force on the charges in the conductor. So this will happen as you move this, this piece of metal through the magnetic field. The charges are going to separate until the forces are balanced. So they're separating until the magnetic force upward is equal to the electric field, excuse me, the electric force downward. And at that point, it will reach equilibrium, and so the charges will no longer move. Let's talk about what that looks like. Once the charges are no longer moving, we know that force E, so magnetic force, you could also put an M there, is equal to force E for electric force. You can also put a C there, I guess, for Coulomb force. And we know that the magnetic force is equal to Q times V, so charge times velocity times magnetic field. And the electric force is equal to Q times the electric field, so the charge times the electric field. Now we notice that our charges cancel, and we get an expression for the electric field, which is velocity times magnetic field. So I've written that out right here. I just wanted to put it in an easier format. Gotta put all my little vector arrows on here. And then we also know that change in potential is equal to the electric field times the position in the electric field. Well, in this situation, for some reason, we use a different letter for position. So D is basically just L. So our change in potential is equal to E electric field times position in the electric field. And I'm going to take this expression for electric field and I'm going to plug it into this equation. And that gives me delta V equals velocity of the conductor times the magnetic field times the length of the conductor. And usually a curvy E, an epsilon is used instead of delta V. And I think those are pretty much just used interchangeably, so that's a good way to think about it. But this is called motional EMF. So this is EMF due to a wire's motion through a magnetic field. And remember, EMF used to stand for electromotive force, and then people were like, well, it's not really a force, so we'll just call it EMF. But it's basically the potential difference that's created on the top and bottom of this wire. This equation is on the AP equation sheet, and so you will have access to that. Just make sure you know what all those terms mean. Now let's talk about what happens when the charges have somewhere to go. So in the last example, we just had a piece of metal moving through the magnetic field. But now let's say that we have these black lines here are metal bars, and this bar right here is like rolling or sliding across this U bar or C bar that's down here. Since it's moving through the magnetic field, the charges are going to be moved in it. They're going to be pushed by the magnetic field, but this time, instead of just gathering at the top and gathering at the bottom, the charges will be able to move because there will be a circle. So I can use my right-hand rule to determine what direction the charges are going to be moving. So if I take my thumb in the direction of the velocity of the wire, my fingers go in the direction of the magnetic field, which is into the page, and then I can see that the positive charges are pushed upward in this wire. Well, they're pushed upward in this wire, and then they have here that they can go here in this loop. So they're going to go this way, and then come back this way, and then come back this way. And so they're going to be moving in a circle. We know that so we use the right-hand rule to determine the direction of the current. So we know we have Ohm's law, which is current is equal to delta V over R. And in our last page, we saw that delta V, or motional EMF, is equal to velocity times L times magnetic field. So now I have this equation here for my current in this situation where we have a bar moving through a magnetic field and the charges have a place to go. I'm just going to write out right here just so that we're going back to it, we can remember what it is that we did. So we're plugging that in right there. So we know that a magnetic field exerts a force on a current carrying wire. So we're going to use the right-hand rule to determine which direction this force acts. So now let's think about the current carrying wire. So here's my my current carrying wire. I'm going to use my right-hand rule, which is F equals B I L. So we've already done some work with that equation. And if I put my thumb in the direction of the current, my fingers in the direction of the magnetic field, my palm will push in the direction of the force. So I get a magnetic force that is to the left. And so the force is to the left. So I'm going to write here, thumb is the current, fingers are magnetic field into the page, and then your palm is the force. So this is force to the left. So so that's very interesting. Now this is just a piece of what this is kind of the intro to talking about induction. Well, this is induction. So what if we wanted to pull this bar at a constant rate? Because this bar is moving at a velocity to the right, but the induced force from the current that's induced in this wire is to the left. So it's opposing that motion, which is an important thing that we're going to see a lot of. So what if I wanted to move this bar at a constant speed? That's going to take a force because there's a magnetic force opposing the motion. So let's figure out what that force is. So we know that the force of pull, wrote it P before a force. That's going to be too big. Okay. So force pull, so the pull force that you have to give is equal to the magnetic force, which is equal to the magnetic field times the current times the length. Now we also know that the current from up above is equal to V velocity times the length times the magnetic field divided by the resistance. So if I plug that into there, then I get the force pull is equal to, let me just write it out so that we're very clear as to what we're doing, instead of just jumping into simplifying it. Okay, so we get V times L squared times B squared over R. So this equation is not on the equation sheet, but the two equations that you use to derive it are on the equation sheet. So this is definitely something that you could have to figure out on the AP exam. So that's the force required to pull that bar at a constant speed. Okay, so let's talk about magnetic flux. Magnetic flux is a challenging concept. I think one of the main reasons is this word right here, flux. If you think about what flux means in society, flux means change, right? But in physics, magnetic flux is not a change of something, it's just a value. So, but we are going to be interested in changes in magnetic flux to calculate things. So it's kind of challenging to wrap your head around. So magnetic flux is the amount of magnetic field passing through a loop. And it depends on several things. It depends on the strength of the magnetic field. So a stronger magnetic field will have more magnetic field passing through a loop. It also depends on the area of the loop, the effective area of the loop. So if this magnetic field is perpendicular to the plane of the loop, then that would be the maximum area. But it could also be, this is hard to show you on a two-dimensional screen, but the loop could also like tilt. You know, like you could take a hula hoop and hold it vertically. If the magnetic field is going horizontally, then the angle between the plane of the field of the hula hoop and the magnetic field is perpendicular. But if you start tilting the hula hoop to more horizontal, then fewer of those magnetic field lines are going to go through the hula hoop. So we call this the effective area. We could also have a loop that could like shrink and get bigger, and that would affect how much magnetic field went through the loop. So the effective area is A times cosine theta if theta is between magnetic field and a line perpendicular to the plane of the loop. Or you'll see it as a sine theta, which is where theta is between the magnetic field and the plane of the loop. The symbol for magnetic flux is a phi, or phi, and it is a vector. So this is a Greek symbol. The unit is a Weber, and a Weber is equal to a Tesla times a meter squared. Magnetic field times area. So this is the equation that you will see on your AP equation sheet, and it is flux is equal to magnetic field times area. Now, the equation sheet doesn't have effective area on there, it just has area. But it's important to note that that area is going to be dependent on the angle between the magnetic field and the plane of the loop. So let's talk about why flux is important. We have two laws that we're going to talk about. The first is Lenz's law. Lenz's law tells us that the current is induced in a loop of wire when the magnetic flux through the loop changes. That's not what Lenz's law tells us, actually. I just was a little ahead of myself. We know that. Lenz's law tells us the direction of the current. So here's Lenz's law. There is an induced current in a closed loop, a closed conducting loop, if and only if the magnetic flux through the loop is changing. That key word here is changing. So you're going to look for flux to be changing. The direction of the induced current is such that the induced magnetic field opposes the change in flux. So when we did our example with the bar sliding across the U-shaped thing, it was moving across through the magnetic field. That induced a current. That induced current created a new magnetic field, and that new magnetic field, the flux, opposed the change. So let's go up and look at this. So here I have this bar. This bar is moving to the right. The magnetic flux in this loop is increasing. It is down into the page or into the screen and increasing because the area is getting bigger as this bar slides this way. So that tells us that according to Lenz's law, the induced magnetic field induced by this current is going to oppose the change in the magnetic field. So if this magnetic field if the magnetic flux is down and increasing, that means the induced magnetic field is going to be up. So you're going to use your right hand rule and you're going to point your thumb up. And your thumb represents the magnetic field in the middle of the loop. And then your fingers curl in the direction of the induced current. So the induced current is counterclockwise, which is what we found when we thought about it a different way. So we could have used Lenz's law for that one. So let's think about 4 ways that flux can change. The magnetic field through the loop changes, so it's either getting stronger or weaker. The area of the loop changes. The angle between the plane of the loop and the magnetic field changes, or the loop moves into or out of the magnetic field, which is a very common problem on AP where they have a loop of wire on a cart and it goes down a ramp and goes through magnetic field. So let's walk through one example or another example of this. So let's say that I'm going to take this magnet and I'm going to move it down into this loop of wire. We know that the current induced by the changing magnetic flux generates its own magnetic field, which opposes the change in the flux. So 1, I move the magnet down. 2, there's an increasing magnetic field in the loop. That causes the flux to increase. So I'm moving the magnet down, meaning the flux is increasing and down. So the induced magnetic field is going to be up to oppose that change. The change is down and increasing, so to oppose it, I'm going to have it be up, my induced magnetic field. Then I can use my right hand rule. My thumb is up, my fingers curl in the counterclockwise direction, and that shows the direction of the induced current, which is shown by Lenz's law. Now let's talk about Faraday's law. In order to determine the actual amount of current or amount of EMF, we are going to use Faraday's law. So the EMF is equal to the change in flux divided by the change in time. So it's the rate of change of flux. This only tells us the magnitude, it does not tell us the direction. To figure out the direction, we have to use Lenz's law. So magnitude of EMF is equal to the rate of change of flux. You will occasionally have a problem. So this equation is on the AP equation sheet. This equation is not, but this would just be if you had flux per coil and you had multiple coils. But usually you'll just be given the flux for the entire thing altogether. So let's do an example problem. Here I have a loop of wire that measures 0.35 meters by 0.75 meters, is halfway out of a magnetic field. with the strength of 0.55 t and traveling with a velocity of 3.1 meters per second. The resistance of the wire is 0.23 ohms. So if I think about what I have going on here, let's draw a picture of it. I've got a magnetic field that is into the page. Take me a while to draw all these X's. And let's pretend that these are evenly spaced, showing a constant magnetic field, or uniform magnetic field, I should say. Then I have this loop of wire, and my loop of wire is here. And it is moving with a velocity of 3.1 meters per second. And it's moving out of the magnetic field, although that's not exactly explained, I don't think, in the problem. And okay, so the first question is, find the force required to maintain the velocity of the loop. So to do that, we know that the force is equal to B times I times L. So this is the force on a current carrying loop. Now we can figure out what direction the current is going in this loop of wire using Lenz's law. So if we think about the magnetic field is down and it's decreasing because the loop of wire is leaving the magnetic field. So since it's down and decreasing, the induced current that is going to induce a magnetic field that is opposing that change. So if it's down and decreasing, the induced magnetic field also needs to be down. So if you point your thumb down or into the screen, you should curl your fingers and you should see that the current curls in the clockwise direction. So the current is going to go in this direction. This is the induced current. So what we are thinking about is the force on this wire right here, because let's use our right-hand rule to figure out the force on each part of the wire that's in the magnetic field. For the top wire, the current is going to the right. The magnetic field is into the page, so the force, let's make this, so the force here is up. On the bottom part of the wire, you have your current going to the left, your magnetic field is into the page, and so your force is down. So these are going to cancel out. So all we're going to care about is this section of wire. And in this section of wire, our current is up, our magnetic field is into the page, the force is this way. So this is just my wire moving in a magnetic field. And the force is equal to the magnetic field times the current times the length. Now I also know that my current is equal to delta V, or EMF, over R, and delta V is equal to the velocity times the length times the magnetic field. So I'm going to put this into there and then this into here. And you get force is equal to B squared L squared V over R. So then we can plug in numbers and we get our magnetic field is 0.55 Tesla. I didn't write out all my notes, which was a mistake. Times the length of the wire, which is 0.35 meters squared, times the velocity, which is 3.1 meters per second. And then we divide by the resistance, which is 0.23 ohms. So that gives us 0.5 newtons. Now, you might ask, how do those units work out to be newtons? Well, let's just check that out. So we have Tesla squared times meter squared times meter per second times ohm. How does that equal Newton? Well, let's see if we can play around with this. So we know that an ohm is equal to a volt per meter. Sorry, volt per amp. I don't know why I said volt per meter. I said it, I was like, that's not right. And so that will help us a little bit. We're going to plug that into there. And then we also know that a Tesla, if we use the equation, force equals BIL. If we isolate for B, we get force over IL. So a Tesla is equal to a Newton divided by an amp times a meter. So I can plug that into there, and that gives me newtons squared over amps squared meters squared times meters squared, well, that's meters cubed, divided by an ohm, which is a volt over an amp. So we're going to put the volt down here and the amp up here, times this divided by a second. Okay, so that got us a little bit farther. One of those two cancels, two of those. One of our amps cancels. And we still have Newton squared meter volt second. So now, let's see here. We have amp times volt. So let's think about power is equal to current times delta V. So this is a joule per second is equal to an amp times a volt. And a joule is a Newton times a meter. So an amp times a volt, which is this right here, is a Newton meter times a second. So I think this is going to work. This is a complicated one. Newtons squared times meter over seconds, and then we're going to divide by AV, so we're going to multiply by the reciprocal of this, so you get seconds, and then newtons and meters on the bottom, and then we get our seconds cancel, and our meters cancel, and one of our newtons cancels, and we're left with newtons. Hooray! Okay, that's all I have for you.